Okay, here's some hints for homework 1. So let a and b be integers with GCD d. Prove that if we divide d out of both a and b, the GCD is equal to 1. Well, okay, so first thing to notice is that these two integers, or what look like rational numbers, really are integers, because d is a divisor of both these numbers. And probably the key thing here is just to introduce some letter for this GCD. So let's just let E be the greatest common factor of A over D and B over D. So these are just a couple integers, and so they will have a greatest common divisor. So what's our goal then? Our goal is to show that E equals 1. Okay, well, what does this mean? If E is the GCD of these two numbers, then E is a divisor of A over D. So E times X equals A over D for some integer X. And E times Y equals B over D for some integer Y. So I'm just unraveling definitions. I introduced E. I've introduced what does it mean to be a common divisor of two numbers. And now from this, let's come back and find a new common factor of A and B. So find a common factor of A and B and prove that E must equal 1 using the fact that D is the greatest common factor of A and B. Okay, I think I've said enough there. On to problem 2. Prove that for any composite positive integer n with, oops, I didn't put in the extra thing here. N strictly greater than 4. We have that n is a divisor of n minus 1 factorial. You immediately see why this would be false for n equals 4. So we do need n to be strictly bigger than 4 in this problem. So hopefully I've got that corrected. Okay, so, well, we're trying to prove that n is a divisor of n minus 1 factorial if n is composite. Okay, so n is some composite number. What does that mean? Okay, so that means n is a product of two numbers, both of which are strictly less than n. So A is trapped in here and B is somehow trapped in here. So that's the definition of composite. N has a non-trivial factorization like this. So now write down what n minus 1 factorial is. Three times 2 times 1. Okay, and so what's our goal? I want to show that n is a factor of n minus 1 factorial. So that means I want to show that A times B is sitting as a divisor of this product right here. And so I claim there are two cases to think about. Case 1, A doesn't equal B. So let's just say A is less than B. All right, well, then look for A and B somewhere in here. Okay, so that case should be pretty straightforward. In case 2, A equals B. Now, in this case, you're going to have A and B both located at the same point in this product. But we need to get that A squared is a divisor of n minus 1 factorial. So I have to find another factor of A somewhere in this product. And where's the next place you would look for another factor of A? Well, if this is A right here, then somewhere down the road there is a 2A. Okay. So by doing that, you should be able to wrap up this problem, and you should see why it's necessary that n be strictly bigger than 4. Use the array method to find the GCD of 423 and 198 and to express it as a linear combination of these two values. So the array method I'll put 423x plus 198y. Put x here and put y here. So when x is 1 and y is 0, we get 423. When x is 0 and y is 1, we have 198. And proceed by performing the Euclidean algorithm on the top two entries. So on the 423 and 198, what would you do in the Euclidean algorithm to find the GCD? Well, the first step is to subtract 2 of these from 423, leaving the 198 alone. And so up in the array, we'll take column 1 and subtract 2 times column 2 to produce whatever this is. So that'll be 423 minus 2 times 198, and you just calculate that and you get some number up here. And then do the same thing in these entries. Column 1 minus 2 times column 2 would give you 1. 0 minus 2 times 1 would give you negative 2. That would produce this number as a linear combination, and proceed like this. And so you keep going just as you would in the Euclidean algorithm until you finally get a 0 in one of your entries, and then the GCD is sitting here as in the previous one. Okay, so we have a completely worked out example in the lecture notes you can look at. And then the array method can be applied in problem 4 with 3 numbers. So I put 105x plus 42y plus 30z, x, y, z, and then if x is 1 and y and z are 0, we would start at 105. Here we get 42, and here we would get 30. And now when you're doing GCDs with more than 2 numbers, you can proceed in many ways. And you are free to do it any way you like. You just keep subtracting multiples of smaller numbers from the bigger numbers. So in the first step, I might subtract, 2 of the 42s from 105, or 3 of the 30s from 105. Take your pick. It doesn't really matter. So if we call this column 1, column 2, column 3, yeah, let's do 3 of these. Okay, so what we're doing in the GCD is subtracting 90 from 105 to get 15, and then I could subtract 30 from 42 to get 12. So I wanted to get 15 here by subtracting 3 of these from there. So column 1 minus 3 of these, column 1 minus 3 of those, column 1 minus 3 of these, and then do the same thing to get 12 by going C2 minus C3. And again, you just keep going until you would get 0, 0, and then some number down here. And you'll see the value D appearing up here. And then the X, Y, and Z values will be right below it. Okay, problem 5. Prove that the ring of Gaussian integers is a Euclidean domain with respect to the mapping delta, given by delta of a plus bi is a squared plus b squared. So hopefully you'll recognize that the delta function is, I don't want the eraser, is just the absolute value. So delta of a plus bi is the absolute value of a plus bi squared. And so you can use standard properties for the absolute value of complex numbers. So if u and v are complex numbers, then delta of uv would be the absolute value of uv squared. Now this is a multiplicative property, so you get delta of u, delta of v. So that's a useful property to keep in mind when you're working through this problem. That's true for any complex numbers, this multiplicative property here. Okay, so to show something's a Euclidean domain, there's 2 properties that need to be verified. First of all, we have to show that delta of u is less than or equal to delta of u times v. And I claim that's straightforward. Just use this absolute value property right here, and it should just pop right out. And then property 2 is the division algorithm. So we have to prove that, I didn't erase all of this mess. If we divide 2 complex numbers, well, okay, this is just some hint here. So let's just go back to actually what it means, the division algorithm. So I let say u and v be Gaussian integers, and I want to think about what is z divided by w. Okay, so let z and w be Gaussian integers, and I'm thinking to myself, let's find z divided by w, and what's the goal? So the goal is to show that z divided by w is some quotient plus a remainder that's very small. So I want to show that z is q times w plus r for some Gaussian integers where the remainder r is smaller than the divisor w. And what does that mean? It means that either the remainder r is 0, or smallness is measured by the delta function here. So delta of r is less than delta of w. Okay, so that's your goal, is to produce these Gaussian integers q and r satisfying this constraint. So now let's work backwards and say, well, what does that mean? Well, that's equivalent to showing that if I take z and I divided it by w, it would be q plus r over w. Q is supposed to be a Gaussian integer. And just think of these other two numbers as being complex numbers. So this is some complex number here, and this is some complex number here. So if I draw the complex number plane, and then you think to yourself, aha, there's the Gaussian integers that are just points like this in the complex number plane. Okay, so that's what zi looks like, these discrete points. And somewhere in this plane we have z over w, this complex number. So maybe it's right there. And your goal now is to produce q and r. Okay, so I want to say that this complex number z over w is some Gaussian integer q plus a small remainder part right here. So you pick q to be the closest Gaussian integer, and there would be a good choice for q, that point right there. So that's a Gaussian integer, and this little difference right here would be this extra piece r over w. So I can define q to be the appropriate lattice point, Gaussian integer right here, and then how big would r over w be? It's going to be pretty tiny, because these are little boxes that are 1 by 1 boxes here. Every box in this grid is just 1 by 1. So what can you say about the size of r over w? So delta of r over w is less than what? And then use that fact to work backwards and get this condition right here. Okay, I'll let you play with that. Problem number 6. If A divides C and B divides C, and A and B are relatively prime, then A times B is a divisor of C. So I want you to prove this without using the fundamental theorem of arithmetic. So it's probably best to think about it in terms of prime factorizations. Since A and B are relatively prime, they have distinct prime factors, and therefore the product A and B is still going to be a divisor of C. But let's not use FTA, the fundamental theorem of arithmetic. You can use either one of these two theorems. Okay, so let's lay out the hypotheses. A is a divisor of C. It means that A times U equals C. B is a divisor of C means B times, say, V equals C. And then AB equaling 1, well, we could use GCD LC and say AX plus BY equals 1. And of course, I'm just being very terse here. When you write up a formal proof, you'll want to introduce these variables as you go along. But I'm just laying out the ingredients. Let's state our goal. Goal AB divide C. That is AB times some integer equals C. Okay, there's a couple approaches we can take. Okay, the first approach, let's use GCD-LC. So I'm going to start with 1 equaling AX plus BY. And I want to get C equals something. So I'm going to multiply by C. And then substitute appropriate things until we see this factor of AB popping out. So that's one approach. Second approach is to use Euclid's lemma. So where do I start? Let's just start with C equaling A times U, for instance. And then B is a divisor of C would mean B is a divisor of A times U. Aha! Now use Euclid. Because what's the hypothesis you need for Euclid? B and A are relatively prime. And we've got that hypothesis stated right here. A and B are relatively prime. So Euclid tells us what, and then make a substitution, and again get down to A times B is a divisor of C. So you avoid the GCD-LC theorem altogether. Number 7. Prove that every rational number has a unique expression in reduced form. A over B, with the denominator positive and A and B relatively prime. So there's an existence and a uniqueness part. So existence part A and B relatively prime, and I say use problem 1 for instance. Okay, so what is problem 1? That's the problem that said if A and B have a common factor D, then when you divide out the D, the GCD is 1. So just think about in practice, how do you reduce a fraction? If somebody gives you 30 over 16, and I say reduce this to a fraction in lowest terms, you want to find any common factor of top and bottom and just divide it out. So you first of all spot a 2, and so I divide the top and bottom by 2 to get 15/8. And then I have a 3 times a 5 up on top, and 2's down below, and so we have it reduced already. So just basically mimic that process using problem 1 and taking an arbitrary fraction A over B. Okay, so uniqueness. Okay, so in uniqueness, we suppose that there are two different reduced forms. A over B equals C over D. So suppose A over B is C over D, with both fractions being reduced and both denominators positive. And what's the goal? So uniqueness means that if this is true, then the tops have to match up and the bottoms have to match up. So there is only one reduced form. Well, okay, so the first thing you want to do is clear out all the denominators. And if you've done that, you are off to a good start. So AD equals BC. And now I gave you this hint. Think of Euclid's lemma. So A is a divisor of B times C, which implies, and now use Euclid. What's that going to mean? After all, at this point, we have the assumption that A and B are relatively prime. Okay, so make a conclusion here, what Euclid says, and then come back, substitute it in, to do that. Or, no, you don't even need to substitute. I think it's cleaner probably just to use symmetry. So next, use symmetry similarly. You'll say maybe that C is a divisor of A times D, which implies by Euclid what? Okay. Try that out and see where that heads you. Problem 8. Prove that the GCD of A and A plus 2 is 1 or 2, according as A is odd or even. And I would just remind you of one fact here, the GCD invariance property. And that's true for any integer q. So just use that invariance property and just pretend you are going through a Euclidean algorithm and calculating the GCD of these two numbers. And it should pop out very quickly. Homework 1, problem 9. Prove that for any positive integers a and b with b positive, strictly bigger than 1. You need strictly bigger than 1 so the logarithm to the base b is defined. A and b are relatively prime. Prove that log to the base b of a is irrational. Okay, so you've probably seen proofs that some numbers are irrational, and what's the standard technique you use to prove something like that? So this is called proof by contradiction. So let's suppose the opposite of what we're trying to prove. Okay, so again, we start with positive integers. B is greater than 1. AB equals 1. And we want to assume the opposite. So suppose S and P. That's my abbreviation for suppose. Suppose log to the base b of a is rational. That is, log to the base b of a equals some fraction r over s with r and s integers. And what can we say about those integers? Well, every fraction can be written in reduced form. So we may assume that R and S are relatively prime, and that S is positive. Okay, well, now all we have to do is remember what the definition of logarithm is. So take the logarithmic form and say, well, what does that mean? That means the base to something equals something. Rearrange the equation a little bit and come up with a contradiction using the fact that A and B are relatively prime. So go dot, 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 get a contradiction using the fact that A and B are relatively prime, and perhaps you want to use that R and S are relatively prime as well. That may or may not be necessary. You can see how that works out. And problem 10. Prove that if P, Q, R, and S are primes with P less than Q, R less than S, and 1 over P plus 1 over Q is 1 over R plus 1 over S, then in fact this is exactly the same two fractions we're adding up. So P and R are equal, and Q and S have to be equal. So it's a uniqueness of reciprocal sums of two primes. Right? So what's the first thing you might think of doing here? Why don't we clear out all the denominators? So if I just clear out the denominators very quickly, you'll get an equation that says P plus Q times RS is R plus S PQ. All right, so you can think about how I got that. So what is the GCD of P and P plus Q? What common factor do those two have in common? So again, just use the GCD invariance property or subtraction principle, and you can find what that equals. And then once you've found that, you can use the fact, P is a prime, and come down to say, therefore P has to divide RS. Think about what allows you to do that, which means P is a divisor of R, or P divides S, one of those two things. Okay, so we have that fact, and then by symmetry, and then what does that mean? If these are primes, that would mean what? If P is a divisor of R, that means P equals R, or P equals S. Similarly, Q divides what? So Q equals what? And then use the fact that P is less than Q and R is less than S to wrap things up.